Welcome students to another lesson of physics in class 9. Today we will begin a new lesson that is on gravitation. We have already discussed about force that is responsible for any type of motion. Today actually we'll be studying about a type of force, that is gravitational force, that is so responsible for holding every single object on the surface of this planet Earth. It is responsible for so many things that we observe around us. One by one we will be discussing about all of them, but let's begin this chapter with a very special understanding about how Sir Isaac Newton formulated this very important law. Let me tell you that this law was formulated in the year 1687. Newton's law of universal gravitation was a turning point in physics. While the legend of the apple falling on his head is an exaggeration of the truth, Newton did have a brilliant insight that every object in the universe attracts every other object. The force of attraction between two objects depends on only two things: the mass of the objects and the distance between them. So, more massive objects exert a stronger force, while more distant objects exert a weaker force. Newton was able to formulate a simple equation to describe this. As you can see in the picture that is coming on your screen right now, that the force is equal to Newton's gravitational constant, that is given by capital G, multiplied by masses of the objects, then divided by the square of the distance between the object. What's remarkable is that the law truly is universal. Not only can it predict how things move here on Earth, but it can also predict the movement of the moon, planets, stars, and even galaxies millions of light years away. Newton believed that the movement of every object in our universe could be predicted. We know now that while this theory generally holds true, it is not precise. Einstein's theory of general relativity had to step in to fill the holes. But still, that doesn't lessen the importance of this law. Universal law of gravitation helps us in the analysis of so many things, so many observations, as I was telling you, and one by one we shall discuss all this. But let us now try and understand how this law was given, what is the basic formulation of this law, and then we will be discussing a couple of problems that could be easily solved using the mathematical formulation of Newton's law of gravitation. Isaac Newton's big idea. Isaac Newton had a lot of brilliant ideas in his lifetime, and a massive one was the universal gravitation. Universal gravitation is not just the fact that objects on Earth fall to the ground. His big idea was that all objects in the universe attract all other objects. An apple may or may not have hit him in the head to cause this revelation. While the apple is probably not true, it's not far from the point. Isaac Newton questioned two things. Why would object on Earth fall to the ground while the moon continued in its circular path? Actually, Sir Isaac Newton realized that both the apple and moon are really falling. The earth follows the rules of the rest of the universe. The apple is starting from rest and being attracted to the ground. The moon has inertia, which normally would make it continue forward, but the attraction to the earth makes it fall. The combination of forward motion and falling gives the moon its orbital path around the earth. So any object with mass m1 is attracted to any other object with mass m2. This is universal, as the name says, meaning all objects. This means that all objects present in this entire universe attract each other. There is an attractive force existing between all objects present in this universe. That is why this law is given the name of universal law. It is called Newton's law of universal gravitational equation. The amount of force depends on distance d and related by the universal gravitational constant g. G is having a value of 6.67 into 10 to the power minus 11 Newton meter square per kg square. So let us get into the expression for Newton's law of gravitation. Actually, the expression for Newton's law of gravitation is given by F equal to G m1 m2 by d square. Let us quickly derive it. So according to Newton's law of gravitation, if we denote F as the gravitational force existing between two objects of masses m1 and m2 that are separated from each other by a distance r, then F is proportional to the product of the masses, that is F is proportional to m1 m2. It is a direct proportionality, and F is inversely proportional to the square of the distance between them. Now how this inverse square law was obtained, that will be discussed a bit later in the coming sessions. We will be discussing how Sir Isaac Newton was able to derive the inverse square law. But for the time being, you should understand that the force of attraction existing between any two objects in this universe is directly proportional to the product of the masses. If we denote the masses with m1 and m2, then F is proportional to m1 m2, and it is inversely proportional to the square of the distance between them. Now combining these two equations, we get F proportional to m1 into m2 by r square. Now whenever we want to replace this proportionality sign with an equal to sign, we introduce a constant of proportionality. So in this case, this constant of proportionality is given by G, capital G. So obviously the expression now becomes F equal to G times m1 m2 by r square. This is the expression for the gravitational force existing between any two objects present in this entire universe. Now since this law is applicable to all the objects present in this entire universe, that's why this law is having so much importance, and it is called the universal law of gravitation. I would like to tell you once more that G is called universal gravitational constant, and it is having a value of 6.67 into 10 to the power minus 11 Newton meter square per kg square. This is the numerical value for universal gravitational constant. Now how to define G? How to define universal gravitational constant? Let's get back to the expression for the gravitational force of attraction. It is F equal to G times m1 m2 by r square. Now let us make G the subject of the formula. This means if I rearrange the terms, I will get G equal to F r square by m1 into m2. Now let us consider a condition. If we consider m1 to be equal to 1 kg, m2 to be equal to 1 kg, and r to be equal to 1 meter. This means we are having two objects, m1 and m2, both of masses 1 kg, and they are separated from each other by a distance of 1 meter. Now when I am talking about the distance of separation, the distance is always considered from the center of one object to the center of another object. So the distance between the centers of these two objects is taken as 1 meter. So we are considering two unit masses separated by a distance of 1 meter. Let us substitute these values in the expression for G. So what shall we get? As G is equal to F r square by m1 into m2, so we will get, on putting the values of m1 m2 and r, G will be equal to F into r is 1 meter square, m1 is 1 kg, and m2 is also 1 kg. So obviously numerically G will be equal to F, isn't it? Numerically, because you can see 1 and 1 that will get cancelled out. So numerically, G will be equal to F. So how to define G? So we define universal gravitational constant as it is numerically equal to the force of attraction existing between two unit masses separated by unit distance. Universal gravitational constant is numerically equal to the gravitational force of attraction existing between two unit masses separated by unit distance or kept at unit distance from one another. And as we all know that G is having a value of 6.67 into 10 to the power minus 11 Newton meter square per kg square. Now let us try and understand how the value of force is going to change with mass and distance. Sometimes these sort of questions are asked in the examination, that if there is a change in the mass of the object, or if suppose the distance between the masses taken into consideration is changed, how will the value of force going to change? So let us consider some examples. Suppose we write down the general expression for force first of all. G is equal to F is equal to G times m1 m2 by r square. So if mass is doubled, suppose the masses are doubled, both the masses are doubled, what change will be observed in the force? So obviously now we will be writing down F equal to G. Since the masses are doubled, so I will be writing 2m1 into 2m2 divided by r square. So this will give us 4 times G m1 m2 by r square. Obviously the force has changed. So now I can write down this is to be equal to 4 times F. You can see the bracketed term G m1 m2 by r square is actually equal to F. So you can see when the masses have been doubled, both the masses have been doubled, the new force of attraction existing between the two masses is 4 times the previous value. This means there is a direct change. If the masses increase, the force of attraction will also increase. So I was already telling you in the beginning of this session that the force of attraction existing between two objects is visible only when the masses are huge. That is why it is difficult to observe the gravitational force of attraction between two masses having smaller values. We are not able to experience this force of attraction even though it is existing between any two objects present in this entire universe. You might be wondering that if we consider ourselves and we are standing in front of a huge multi-storied building, then as per this law, that building and between that building and us there is a gravitational force of attraction, but still we are not able to experience it because even that value, the value of that huge building, is also not good enough to realize this gravitational force of attraction. So when will this force of attraction visible to us? When the mass is as huge as the mass of this planet on which we are living, the mass of Earth. Do you know what is the mass of Earth? Mass of Earth is 6 into 10 to the power 24 kg. So just imagine if we are having an object as huge as this, then we will be able to experience the force of attraction. Earth is able to experience the force of attraction, the gravitational force of attraction of Sun, because Sun is much more heavier than Earth. Do you know what is the mass of Sun? Mass of Sun is 2 into 10 to the power 30 kg. So in these cases we are able to experience the gravitational force of attraction. Let us also try and understand how force is going to be dependent on distance. So again I am writing down the general expression for force. F is equal to G m1 m2 by r square if distance becomes half. This means if the two objects were separated by 1 meter, now they are separated by 1 by 2 meter, distance becomes half. What change will it produce on force? So the new force, remember, distance has become half. So I will write down r by 2 whole square, isn't it? So how to write it down? F dash will be equal to g m1 m2 by r square by 4. Now that 4 can be taken to the numerator. So now we can write down f dash equal to 4 times g m1 m2 by r square, and again this bracketed term is equal to f. So you can see that if the distance decreases, force increases, and it is quite obvious, if the two masses are kept close to each other, then the gravitational force of attraction is going to be more strong. If the distance is increased, the force is going to decrease. Let us take one more example. If r is doubled, then f dash will be equal to g m1 m2 by 2r square, isn't it? Let's solve it out. So f dash will be equal to g m1 m2 by 4r square. We can write it down as 1 by 4 times g m1 m2 by r square. Again you can see we get therefore f dash equal to f by 4, because the bracketed term is equal to f. So when the distance decreases, the distance between the two masses decreases, then f increases. The gravitational force of attraction is going to be more. And if the distance is increased, then the gravitational force of attraction will decrease. So now you can understand that if there is a change in the value of mass or distance, it is going to produce a proportional change in the value of the gravitational force of attraction existing between the objects. Let us see the universal gravitational distance to force graph. This is the type of graph. If we plot a graph between force and distance, as I was right now discussing, that as distance increases, the gravitational force of attraction decreases, and vice versa. So if we plot a graph between the value of distance between the two masses m1 and m2 and the value of force, then this is the type of graph that is going to be obtained. We can do a little bit of rearrangement and obtain different expressions for masses. In this manner, we can obtain different expressions for distance and mass. Now, as I was telling you, we'll be discussing some problems. So what is the force of gravity between the Earth and the Moon? Earth's mass is given 6 into 10 to the power 24 kg. Moon's mass is 7.35 into 10 to the power 22 kg. Distance between Earth and Moon is 3.844 into 10 to the power 8 meter. So using the given values and then putting these values into the equation for gravitational force, see, we get the value of force of attraction existing between Earth and Moon to be equal to 1.99 into 10 to the power 20 Newton. It's a huge value, and that is the reason why you find Moon revolving around Earth. Now here I would like to clarify one question. There might be a doubt in your mind that we have learnt about Newton's third law. To every action there is an equal and opposite reaction. So if Earth attracts Moon, Moon also attracts Earth. Now to every action there is an equal and opposite reaction. So this means the force existing between Earth and Moon are going to be similar. So why is it so that Moon is revolving around Earth and not the opposite? Why can't Earth revolve around Moon? The reason behind it is that the mass of Earth is large as compared to the mass of Moon. Just now you have seen the value of mass of Earth. Mass of Earth is 6 into 10 to the power 24 kg, but mass of Moon is 7.35 into 10 to the power 22 kg. So obviously mass of Moon is around 100 times less than the mass of Earth. Due to this huge mass of Earth, the acceleration produced in Earth is smaller as compared to the acceleration produced in Moon. That is the reason why Moon is revolving around Earth. In a similar way, we can understand why Earth revolves around the Sun. The force existing between Sun and Earth is same, but still Earth is revolving around Sun because Sun is heavier than Earth. So the acceleration produced in Sun is much smaller when it comes to the acceleration produced on Earth. So that is the reason why we find Earth revolving around Sun and not the opposite. How much will the force of gravity change if you double one mass and quadruple the distance? Now this is one type of question that we were discussing right now. By changing the value of masses and distance, we can figure out how the force is going to change. Again, what is the force of gravity between Earth and Mars? In a similar way, you can substitute the values of m1 and m2. Take m1 as 5.972 into 10 to the power 24 kg. Take m2 as 6.39 into 10 to the power 23 kg. Substitute the values for distance, that is 5.46 into 10 to the power 10 meter. Using the formula F equal to g m1 m2 by d square, you get the value as 8.54 into 10 to the power 16 Newton. So in this manner, we can solve some numerical problems using the expression for gravitational force of attraction. These are similar sort of problems. I will suggest you to solve more number of problems using any reference textbook. So in this manner, you can get some idea regarding what is the gravitational force of attraction between different objects and why is it so that this force of attraction is not observable most of the times. I would like to mention one more time at this stage that this force of attraction is the weakest force of nature. Amongst all the fundamental forces existing in nature, actually the gravitational force of attraction is the weakest force because it is dependent only on the masses and it is observable only when the masses are huge. With a very simple equation, Sir Isaac Newton was able to give an explanation, a satisfactory explanation to so many things. So what are the applications? What is the importance of universal law of gravitation? With the help of universal gravitational law of attraction, we are able to explain how we are able to experience our weight. Now you might have seen the astronauts, they are just not able to experience their weight. There is a situation of weightlessness and they keep on floating in air inside a spaceship. This is primarily due to the reason because of the absence of gravity. In the absence of gravity, everything will start flying. We would just not be able to hold ourselves on the surface of this planet. So we are able to experience our weight. We are able to remain bound to the surface of this planet due to the gravitational force of attraction existing between us and Earth. So this is the very main application or the importance of the universal law of gravitation. Using the universal law of gravitation, we can understand why Earth moves around Sun, or for that case, why all planets move around Sun. The reason is the gravitational force of attraction existing between Sun and all the planets. We can also understand why the satellites move around Earth, why Moon moves around Earth, due to the same reason. One more phenomena that can be explained using the universal law of gravitation is formation of tides on the surface of seas and oceans. Now tides are formed due to the gravitational pull of Sun and Moon. So this can also be satisfactorily explained using universal law of gravitation. We will end our discussion at this point, and I will suggest you to have a nice reading of the entire text related to this topic so as to have a better understanding of this hugely popular and extremely important law known as the universal law of gravitation given by Sir Isaac Newton. Thank you.